Good afternoon. Today we will learn some defenses against stack buffer overflow attacks and also learn tricks to avoid such defenses in attacking buffer overflow vulnerabilities. And that's why this class is called Cyber Attacks and Defense. We will learn the attacks and defense altogether from now on. Namely, we will learn how DEP, data execution prevention, and stack cookie defeats a buffer overflow attack, and also learn how to defeat these two attacks, these two defenses. And let's do a little bit of logistics first. Shellcode challenges are due today, so you will get 50% points until next week for your late submission. And you can submit your write-up a little late, so it's quite okay to not submitting the write-up at the deadline. But in submitting write-up, please include your final shellcode for short shellcode challenges for having extra credits for the shellcodes shorter than the 12 bytes. And I recommend you to include make obj dump and include that output of that in your write-up, and also a little bit of description about why your shellcode works. And today I released week 4 challenges, and these challenges are due on the May 13th. And let's start with a buffer overflow example. With a buffer overflow vulnerability in a program, we can overwrite stack buffer like this, and at the end we can overwrite the return address to the address of the shellcode like this, and the code inherits a privilege and runs a shell for us. So inheriting privileges with these two system calls, and then run bin-sh at here. Yeah. Then let's think about potential defenses against this attack. Today we will learn two types of defenses. One way to defend this attack is preventing a buffer overflow attack fundamentally. For example, checking a buffer base and bound on every access of the memory, rejecting out-of-bound access to the memory. This defense would be a fundamental defense to the buffer overflow attack, but it could be slowed down the program a lot. Another way to defeat this attack is making exploit difficult instead of fixing the vulnerability or defeating buffer overflow attack fundamentally. And with this way, the defense could be inaccurate, but it could be fast and efficient defense. And this latter one is called as an exploit mitigation, and these are main focuses for defenses and attack today. In detail, we will learn about base and bound check first as a fundamental defense against a buffer overflow attack. Next, we will learn stack cookie as our first exploit mitigation, and then we will also learn data execution prevention as the second exploit mitigation to the buffer overflow attack. Let's start with the base and bound check, which builds up the spatial memory safety in the program. To start with, let me introduce a concept of a fat pointer. And a fat pointer is a pointer that not only stores the target address that it should point, and it also stores a base and bound information to define the start and the end of the memory region. For instance, when we allocate a buffer, for example, using an malloc with size 512, then we can set the pointer A as the address of the allocation, and also with this fat pointer scheme, we can store the base address of A as the allocated address itself, A, and then the bound address as like a base plus the size, A plus 512. And simply, the base and bound points to the allocation base and bound of the memory address A. Then, whenever we access the pointer A, we can apply base and bound check. For example, if we access A0, then it'll be within the base and bound. And if we access A1, A2, or AI up to 512, 11, These are all legitimate because the base and bound will be within this range. However, in case if we access A 512, which is like a 1 byte out of bound of this address region, yeah, then taking the address, taking the index of the 512, and that is bigger than the A bound, then we can detect and disallow the access of it. Likewise, we can also disallow the access of the A-1 because the address value will be below the base address of the A. And having the fat pointer making this kind of the base and bound check, and we can apply this kind of check on every memory access for for defeating the buffer overflow or underflow. And to use that in the C programming language, this technique should have some sort of propagation rules of the fat pointer. So whenever we assign a pointer A to some other pointer B, we not only copy the address A to B, we also need to copy the base and bound information from A to B. And in case if we would like to apply some arithmetic operations on the pointer, for example, taking the address of index 2 of B and assign that to C, then we will transfer the address itself, and also at the same time we need to propagate the base and bound information from B to C. And even if we apply the pointer arithmetic, the base and bound will stay same because it will point to the allocation base and bound. So the pointer arithmetic does nothing with the memory allocation adjustments, so we will just pass the same base and bound. Then if we access C index 1, so now C points to the B plus 2, so maybe somewhere here. So B starts at the start of the A, B plus 2 could be here. And then if we access C1 like this, then it's C is B plus 2, which is A plus 2, and C plus 1 will be A plus 3, and that is definitely within the base and bound. So we can allow access of it. But if we access C 510, then now we know that the C is A plus 2, and C plus 510 is like the A plus 512, which is 1 byte out of bound. Then we can apply base and bound check, and this C bound has been copied from B bound and the C bound, all the same value, the bound of the A. Then we can detect that this access is out of bound, and we can disallow the memory access. And we just have seen how it works in detail, but at the high level, how this can prevent a buffer access. For example, copying a large amount of data to a buffer C using the string copy function. And that is, when the code copies to location of the C510, which is the address pointed by A plus 512, which is out of bound, the code internally can check the base and bound. So we can check that this value is out of bound, then we can detect the buffer overrun. And this is how Java and other memory-safe languages protects buffer overrun, and it is used even in the vector object in the standard template library in C++. So base and bound check can fundamentally kill the buffer overflow attack because it will record base and bound and then apply the check for on the every memory access. And this defense is formalized in 2009 in a paper titled as a softbound, providing a complete spatial memory safety for the C language. In the paper, you can see the rules that we learned and assign the pointer and base and bound, at the same time of the pointer assignment. So we can carry this triplet of the information pointer, base, and bound as a fat pointer, and then propagate this information whenever we have a pointer assignment or pointer arithmetic. And this defense can fundamentally kill the buffer overflow vulnerability. And if applied, there will be no buffer overflow vulnerability at all. Then why do we need to learn about this one? So this has been developed in 2009, and if applied, then there will be no buffer overflow vulnerability at all. Then why do we learn about this? Surprisingly, this defense has not deployed in C and C++ language yet. The reason is that the protection makes the execution of the program too slow if applied. Some examples of the source of the performance degradation is as follows. Whenever we apply operations to a pointer, so in a pointer assignment, or then we need to assign two more values, then there will be additional 2 times of the overhead, actually the 300% in the execution time for the pointer assignment, and even we need the 3 times more storage for storing a pointer, because we need to store the address as well as the base and bound. And also, whenever we access the memory, we need to apply 2 comparisons, and then these will add lots of performance degradation. And it will also affect on the use more cache, more virtual memory, and that will also degrade the runtime performance of the program. And this is the performance benchmark graph of the work softbound, this paper. And then you can see that this will incur around 100% of overhead, which means 2 times slow, yeah. And then the adding around 200 or 300 times of the overhead, which means 3 to 4 times slower for some of the program. So this slow defense can kill buffer overflow vulnerability at 100% accuracy, and that's good. But in practice, it's very hard to pay for the around the performance overhead, which is slower 2 to 3 times. And one of the examples is that the example picture that I put on the slide is taken from the YouTube clip that compares a cell phone booting time when the cell phone manufacturer releases a new cell phone. And this means that the consumers choose a product by its runtime performance. And if one of the phone runs 3 times slower than others, who would like to pay for that? Maybe some people who really cares for the security may like it, but many others who don't care much about security, they would prefer the better performance and or better battery life if they ignore the security about that. So the implication here is that there is a trade-off in security and performance in reality, and for the defenders, it's very important to make a security mechanism that defeats attack while having a good runtime performance, because that will be the key to the deployment of the security mechanism. So researchers came with a clever idea to defeat buffer overflow vulnerability, not like a base and bound check, which is very slow. And the first example of that is stack cookie. The mechanism is very simple. Putting a random number in the stack right below the save DBP and the return address. And if this value, cookie value, has been modified, our return mechanism will kill the program. And this defense is specific to sequential buffer overflow. Sequential means that overriding starting from the buffer and up to the return address, and fully overwrite all the values in between these two. And when we make a function call, how this mechanism works is that when we make a function call, we will put a random cookie value here, and then when the function returns, we will compare this value to the original random value to check if any kind of the overwrite operation has been applied to the cookie and save the ABP and the return address. And if the value is matched, then it's okay. But if the value is mismatched, then we can detect that as an attack and kill the program. And the following is an example of detecting a buffer overflow attack using a stack cookie. At the function call, we stored some random value at here, the cookie position, and then we can supply this much long data to the buffer via string copy. Then the cookie value will be overwritten by the buffer like this, and then it will also overwrite the saved ABP and the return address. And then when the function returns, it will compare the original cookie value to the stored cookie value. But right now, the attack overwrote the value to DDDD, so the value is mismatching. Then we can detect that as an attack. So because the cookie value is not matched with the random value, then we can set the alarm flag and kill the program. And this kind of defense would be much simpler than fat pointer idea because we don't need to propagate and record all the base and bound and then apply such check in every memory access. Instead of that, we can insert the cookie at every function call and check that at every function return. And this defense was formulated by an academic article called the Stack Guard from Oregon Graduate Institute, the school in Oregon in late 90s, which does not exist for now. And how it works is that this is the normal program stack. It has a buffer, local variable, and return address, and the attack will be happening from overriding from the buffer, local variable, and override this return address. Yeah. And then with the defense, the stack diagram could be like this. So we can put a canary word here, the stack cookie in the stack, right below the return address. Then the stack canary word will be overwritten. If we attack from the buffer, overwrite the local variable canary word, then it will overwrite canary word first before overwriting the return address. And if we can detect this value overwritten and has been overwritten and then mismatch it with the original random value we put, then we can detect the attack. And the reason why it is called as canary is that the coal miners in 1800 or 1900, they use this bird canary as like the indicator of the carbon monoxide emission, because this canary, a small bird, die first, even with the low concentration of carbon monoxide, before human workers are being exposed and poisoned and eventually died by the carbon monoxide emission from the coal mine. So if the canary dies, then all the miners should be evacuated from the mine. And to resemble that kind of the alarming signal for some catastrophe, they use the word canary, but pure cute canary. So let's use the word stack cookie instead here. And this stack cookie is deployed in the most compilers, including GCC, Clang, Visual Studio, and many other compilers because it is fast and efficient defense. And if you build the code on the slide using a basic compilation command like this, then you will see the following assembly code. And these two parts are additional assembly code added to compare this, insert and compare the stack cookie. And by reading the assembly code, you can see that the cookie will be stored at the EBP minus C at here and there. And at the function start, it gets the stack cookie value behind the GS register offset 0x14. Get this value, some of the random value stored in this address to the register EAX, and put that to EBP minus C, and clear the EAX value because the leaking this random value will be security vulnerability to the attackers. Yeah. And then at the function return, it will get the can stack cookie value to the EAX register and then apply XOR with the value stored in the GS register. And then JE, this instruction, if two values are matched, so the JE is equivalent to JZ, the jump if 0, and then XOR result in 0 because two values are exactly the same. So if the XOR of the GS at the 14, that random value matches with the stack cookie value, and if that is 0, then it will jump to the input function plus 70, which is a leave and return. And otherwise, if the values are mismatching, then it will call stack check fail, which result in the stack smashing detection like this. The program will die if by the mechanism. And analyzing the performance overhead of the stack cookie information is something like this. So this will insert a 2 memory move and 1 additional compare per each function call, which is far small number than the pointer operations in the program. So it incurs only 1 to 5 performance overhead, depending on how much stack buffer variable you have in the program. So if you do not have much stack buffers object in the functions, then the overhead will be negligible, around 0.3% or something. But if all of your function has the stack buffer, for example, the compilation option fstack protected R means that it will apply this kind of defense to all of the function, then we could have around 5% overhead at worst. And up to this point, I explained the defense mechanism stack cookie as an exploit mitigation to the stack buffer overflow attack. However, this will not be a complete defense, and your first batch of the task in week 4 is to defeat this incomplete but efficient defense with these 4 challenges. And to help achieve that, I will let you know about some of the weaknesses of this defense. First, it will fail if the attacker knows the cookie value. Yeah. So I told you that the assembly code for the stack cookie clears the value in EAX because the leaking this cookie value could be a vulnerability, security vulnerability for the attackers to exploit. Yeah. And then how they can do that is, so for example, suppose we use a fixed cookie value, 11223344 as a cookie value like this. Then the attacker can overwrite save the EBP and the return address without changing this cookie value, because by just writing the same cookie value in the buffer, then attackers can overwrite save the EBP and the return address, but while the cookie value remaining the same. In this case, we cannot detect the attack at all. So in the challenge stack cookie 1, your task is it uses the fixed cookie value, so your task is to avoid this defense by filling the same cookie value in your attack vector and overriding the save DBP and the return address. And in the next challenge, stack cookie 2, it will be a little bit cleverer than that. So it will use the rand function to generate this random stack cookie value, but you can guess the value returning by the rand function. So please guess that value and match the stack cookie to exploit the vulnerability, to stack overflow vulnerability and change the return address. But make sure that you do not modify this cookie value. You need to overwrite that with the same value that the stack cookie stores the random value that stack cookie used by the stack cookie. And next is that the stack cookie can only defeat a sequential buffer overflow attack. That is, because it placed the stack cookie right below the save DBP and the return address, which is in the middle of the stack. So it will only defeat the attack if the attack will overwrite starting from here and entirely up to this point. However, if you can alter the buffer index, for example, if there's a local variable index I, and then that will point to where we access the buffer, then it could eventually overwrite this value too. And if we can change that value to point the out of the index without by skipping the cookie and directly points to the return address or something. So for example, in the one of the challenges, stack cookie 4, it has a buffer size 0x80, but if you change the buffer index to 94 or something, then you can directly overwrite the return address. And you need to perform this kind of attack in stack cookie 4 by not knowing the stack cookie value, not leaking that, but you can skip the overriding the stack cookie part, and you can directly overwrite the return address to exploit the buffer overflow vulnerability in stack cookie 4. And the next weakness is that the stack cookie only has the 32-bit security in the 32-bit machine, because the random value in the 32-bit machine is just a 32-bit integer. So if this random value is generated securely and not being leaked, then the chance that the attacker may guess it and put the same value and overwrite the saved ABP and the return address will be 1/4 billion trial, which seems super secure, right? But the reason why I'm mentioning this as a weakness is that it could fail if the attacker can read the cookie value. But the cookie value is hidden behind the GS register. But even if we cannot read the address pointed by GS register, we can read value on the stack, because that will be stored into the EBP-C. Yeah. So this will kill the attack. So any information leak about the stack is critical to the security. So if there is any kind of the memory leaking to let attackers know this value, then it will not be the one trial over 4 billion. This is a one shot for the exploit, as we did in stack cookie 1 and 2. And moreover, you can break this 32-bit stack cookie with only 1024 trials in some special case. That is, if the program uses a fork for subbing multiple clients. 4 billions to 1024. It's surprising, right? The reason behind this is that when we use fork, the random value cookie will be staying as the same on the stack. That makes a weakness. For example, think about a server program that serves multiple clients. When a client is connected to the server, we will fork the process to serve the child client, and it has the same stack cookie value because the fork will copy the entire memory space from the parents to the child process. And when the next client comes in, we will do fork again, then it will have the same cookie value. And in the third client, the values stay the same because fork will copy the same environment of the server to all of the clients by definition. Then, why this reduces your defense security from 1/4 billion to 1/1024? To prove that, we have a challenge stack cookie 3, which make you to defeat stack cookie defense from GCC Propolis. We make the following assumption for the attack. First, a server contains a sequential buffer overflow vulnerability, and you cannot go across the index as we do in like stack cookie 4. And the second assumption is that the server uses a fork to serve a client. And the third assumption is that the program lets the attacker know if it detected the stack smashing or not. So it will have the error message like this. So if this is printed, then you can regard that your stack cookie modification has failed. But if you match the stack cookie, then you will not see this message. And how we can attack this is that we will guess the cookie value byte by byte. That is, we will not overwrite this cookie value as a whole. Instead, we will overwrite only one byte. For example, buffer overflow could be like this, and we only overwrite the last byte of the stack cookie if this smashes the stack. And if it is, we will increase the value. Because if that shows that stack smashing detected, that means like that we failed on guessing this value. But eventually, if it matches to the original value, 89, then it will not print a stack smashing message at all. Then we can detect that the value has been matched. And then we can guess, so some of the message, this kind of the message will be printing if we guess 0, 1, 2, 3, the value has been mismatched with this one. But if we match the value, then we cannot see this message. So by using that as a side channel, then we can detect if we match the value or not. And then we can move on to the second value. So we will fill the buffer like this. And now we know the last value is 89. And try 0, 0. It will show stack smashing detected. Another value, stack smashing detected. But eventually, if we match the value 55, then it will not printing any kind of error message. So you can use this as a side channel attack, and you can guess byte by byte. So if you do it for 4 times, then you can break the 32-bit stack cookie protection with less than like the 1024 trials. And if it is 64-bit, it's 8 bytes. So it will incur like a 256 multiplied by 8. So within like a 2048 trials, you can break this stack cookie. Yeah. And from this kind of activity, we can learn that the propolis, the stack cookie, is not a complete defense, but it could provide some sort of a protection without impacting a lot to the security. So thereby, we use the defense, but it's incomplete, but it will give some sort of defense. Next is about data execution prevention. This is a different type of defense stemming from a question that what's the attacker's move if they found a buffer overflow vulnerability? That is, attacker would like to jump to the shellcode. Then, why do we let the attacker run the shellcode? What if we block the shellcode execution at all? Then attackers cannot do anything, even if we have the buffer overflow vulnerability. Then, attacker unloads the shellcode in the stack, as you guys are doing for exploiting challenges in week 3. Then stack's supposed to store only the data, not the code. Then why stack is executable at the first place? Then a defense could be making the stack not executable. Then we can prevent the shellcode execution. And this problem stems from the history of the computer architecture. The current computers are built as a von Neumann architecture, which means that there is no clear separation on the data and the code memory. We use one memory space to store the data and the code at the same time. However, in the Harvard architecture, the program code and data they are using a separate memory, so they cannot be mixed at all. So if we use Harvard architecture, we cannot use shellcode because data is not writable. The data which is a writable memory is not executable, and then programs are read-only if supplied at the start of the execution. However, although we are residing in a von Neumann architecture, CPU designers dislike attackers running shellcode, so they included non-executable flag, this one, in the page table entry that controls control and manages the virtual memory access permission. So we can set some part of the program memory as non-executable by setting this bit as 1. If we put 0, then it'll be executable. So for the code area, we can put 0 for the entry, but we can put 1 for the stack or other data area to prevent the execution of the shellcode or any kind of the data injected to the program. So if this bit is set as a 1, then even if we inject the shellcode in the stack and return to there, then it will result a crash because that memory is not executable. And after CPUs, both Intel and AMD includes this feature as a security feature, Microsoft Windows applied this defense in Windows XP SP2 in 2004 with the name of the data execution prevention. And in Linux, this feature is supported since kernel version 2.6.8 since 2004. So this is around a 15-year-old defense. And this DEP, Data Execution Prevention, is a marketing term from Microsoft, and NX, no execute bit, is a marketing term from AMD. So in academia, we call this defense as a WXOR X, which is a writable XOR execute, which means having no memory that is both writable and executable, because XOR could be true when either one of this is true. So memory could be writable, then it will be non-executable, and if the memory is executable, then we can make it non-writable. Then there will be no code injection. Then if there's a no code for setRegID and execCVE in the program, then we cannot run a privileged shell. That's the defense. So to check if the program has an executable stack or not, you can use the command readelf. If you run the command readelf-a, the file name, then it will show the stack permission right like this. So for the GNU stack, you can see RWE, which means readable, writable, and executable. And if you run the same command to the non-executable stack program, DEP-1, the challenge, you will see the permission of the GNU stack as a readable and writable, not executable. Yeah. In such a case, shellcode injection and running will fail. And this is an easy defense and does not incur any kind of performance overhead because memory permission checking is done in hardware in a very, very fast manner. So now the most programs are built with this non-executable stack and default as a defense mechanism. Then, how can we run a shell by exploiting the buffer overflow vulnerability even with this DEP defense is inactive? And can we run this kind of the system bin-sh even if the program does not have such code at all? Yes, we can do that. And because the C library that program includes all such part of the code. So we call this attack method as return to libc. So basically, we will reuse some of the functions implemented in standard libc library, standard C library, and that's called as a return to libc. So we will return to some of the functions in the C library. And before getting to the return to libc, let's learn about how dynamically linked library works. When you build and run a program, you might use some of the functions from the library that you don't implement. For example, printf, scanf, read, write system. These functions you didn't implement it at all, but you can use it. Then a quick quiz. In this regard, where do these functions reside in the program's memory? Number 1, in the program, in the program binary. Number two, in the header file, so it will be compiled with the program. Three, in somewhere in the process memory prepared by the operating system. The answer is 3, and then such functions are pre-mapped in the somewhere in the program's memory by the operating system. And that is done by the how we load the ELF program by the operating system. And when we run execve system call in Linux operating system, it will load the target ELF binary first, and then it will also load all required library program that target ELF requires. And you can check the required library using the LDD command. So if you run the command LDD and supply the file name, then it will show that what kind of library it should load. And you can see that the libc.so.6, which is the entire C library, and it is linked with the program. And this means that all the code of the C library will be available when we run this program. And you can see a more detailed information using the strace command. So strace and run this program, then it will run execve, and then it will also open the libc.so.6 and map that into the program. Like this. And this dynamic library, libc, will include all the functionalities of the standard C and others, such as execve, system, open, read, and write. You can find all these functions. Then, if you know the address of this one, then you can return to this kind of functions, any kind of function, in libc. Then you might be curious about how you can get the address of the system. Because if you can set the return address to the system function, then you can run some other command, maybe cat flag. And you can find the address of the libc functions using gdb. So what we will do is gdb the target program, and we will run print system to get the address of the system. But it will not working if you just run these commands, because your program need to be in an execution state to see the library in the program, because library will be loaded after you execute the program. So what we will do is we set the breakpoint and main and run the program, then it will stop. Then after that you can run print system, then you can get the address of the system in the library. Then the next question is that now you know the address of the system, so you can put this as a return address. Then how can you run system bin.sh with a specific argument? So for example, now you know the address of the system, then if you put the return address as the fill the buffer, save dbp, and they put this as a return address, then this will run the system function at the return. But how can you run the system bin.sh or system a or system cat flag, the specific command that you want to run? To do that, you need to understand how the function call works with the program stack. And I'm sure that you are familiar with this kind of diagram. And we will be focusing not on the local variable side. At this time, we will be focusing on the argument. So this is what regular function looks like. And then from the ESP to EBP, we can store local variables. And EBP 0 will store save dbp. EBP plus 4 will store the return address. Then what are the informations stored in the EBP plus 8 and EBP plus C? So at EBP plus 8, we have first argument of this function, and then EBP plus C will store the second argument of this function. Then what will happen to our program's stack when we call system function by changing the return address? So we will overflow the stack like this, and then at the end of the function, it will leave. So leave will change the EVP to the saved EVP, and then ESP one up, yeah, and then it will return system. Return to system. This should be MOV, not MOP, right? Yeah, return to system. And then in the system function, it will have push EVP. So it will push, save the EVP, and then move EVP to ESP. So it'll be something like this. And then sub ESP. So the stack configuration is something like this. And then now this will access first argument from the EVP plus 8. And then what's in the EVP plus 8? So that's the second argument of the original function will be the first argument of the system. So we can put some of the arguments to the system at this location. And then that's the return address plus 8. So if you want to call system message, then you need to overwrite return address as a system, and then return address plus 8 as the address of the message. Then when running the system, it will fetch EVP plus 8 as the first argument, then that will be the address of the message. Then next, what will happen if the system returns? It will do leave and return. So it will return to BBBB. So it will be crashing, but can we change this to run multiple functions? So return to system and then return to another function. For example, if we set stack like this, then it will leave, return to system, and then its first argument will be message, and then leave, return to printf, and then its first argument will be ASDF. So by composing the stack return address and argument, return address and argument like this, then we can chain and run multiple functions using one buffer overflow vulnerability. So the assignments for the breaking DEP, data execution preventions, are as follows. In DEP 1, you cannot upload and run your shellcode. Instead, you can run some function defined in the program. And it will run some command for you, but you can hack the environment to get the privilege and read the flag by running this function. And in the challenge DEP 2, there is no sum function, so you need to find the system function in the library and call that with the BNSH as an argument. You can do that, and please refer to this diagram to fill the buffer and system and the first argument as the address of the BNSH. And in DEP3 challenge, there is no library at all. That means you don't have the system function. So what you need to do is that you need to call and chain these three functions, sum function, read, and print. And you need to supply all these arguments correctly to solve the DEP3 challenge. So to be more specific, in the DEP3 challenge, the challenge is statically linked, which means that it does not include the libc function at all. So it will not have a system nor execve, but it will have some of the functions that the program uses, printf, read, and other functions. So there is a function called the sum function, and what it does is like that it will open a.txt. And in such a case, you can create a symlink from flag to a.txt, then it will open the flag file instead of the a.txt as a file descriptor number 3. And in this challenge, please run these three functions. First called sum function, and it will open a.txt as a file descriptor 3, and then read from the file descriptor 3 to somewhere in the stack memory for the size 256 or any size longer than the flag size. And then printf that memory. Then it will print out the data that you read from the flag. And by filling the stack like this, first the return address as a sum function, and then read first argument as a 3, some stack address and size, and then call printf its first address as the address that you read the flag content. And this is the first part of the week 4. So today I introduces 2 defense mechanisms, stack cookie and data execution prevention. And your task is to defeat these 2 defenses in 7 challenges. You can see on the BM-CTF1 server. In the next lecture, we will learn how to defeat another defense, address space layout randomization, with 6 more challenges. And these challenges are in a different server in vmctf3.ecs@oregonstate.edu. So you can log in with the same ID, same key, but the domain is different. And all these challenges are due on May 11th on Thursday. So please take enough time to solve the challenges. Thank you.